In this video, I want to talk about sequential logic design, more specifically how we can create latches and flip-flops using System Verilog. So System Verilog uses what is called as idioms to describe latches, flip-flop, and finite state machines. So there are some other coding styles that can simulate a latch or flip-flop, but they usually produce incorrect hardware. So the latch or flip-flop behavior, if it's not done using idioms, that's usually as a result of an error or a glitch in the system. So for defining flip-flops, we use always statements. So the general structure of an always statement is something like this. We have the keyword always, then we have @ sign, and inside the parentheses we have the sensitivity list, and then after that we have the statement that we want to be executed. So whenever an event that is mentioned in the sensitivity list occurs, the statement is going to be executed, but at other times the statement won't be executed. You can think of it simply as an if-else statement, right? But with if and else statement, you have some concept from regular programming, right? For System Verilog, since we are actually making a hardware, right? And we can have things happening simultaneously, using always statement is basically the way to create latches and flip-flops. So let's just take a look at one example. And here I want to create a register that contains 4 D flip-flops. So if you remember from before, a flip-flop had a data input, a clock input, and a Q output, right? So this was the bare minimum for a flip-flop. So what we have here for this module, we have the input as a logic value, only 1 bit as the clock. We have another set of inputs, again logic values, 4 bits, and we call them D. So that means that D basically is D3, D2, D1, and D0. So this basically means that we are designing a register with 4 D flip-flops. And as for the output, we have Q, which is again a logic variable, and it has 4 bits. So now to give the functionality of the flip-flop, we use always _FF, which is the keyword that is being used for defining flip-flops, and then @ sign, and then inside the parentheses, if you remember, we had to have the sensitivity list. So since the flip-flops are sensitive to the rising edge of the clock or edge of the clock in general, this one that we want to create is sensitive to the positive edge of the clock or the rising edge of the clock. So that's why we use this keyword pos edge and then clock. So that means that any time a positive edge of the clock occurs, so when the clock goes from 0 to 1, whatever is inside this always statement is going to be executed. At other times, this won't be executed. So as for the statement that we want to execute, we get Q to be less than or equal D, right? But this is not actually less than or equal. This is resembles an arrow, right? And basically means that gets the value for D. I will talk about this type of a statement later on as well. So as you can see, the implementation of a D flip-flop is very straightforward. We are basically describing the functionality of the D flip-flop. We knew that on the rising edge of the clock, whatever we had in D, it should be stored in the flip-flop, and that's exactly what we have here. We have always FF @ sign, the sensitivity list, which is going to be the positive edge of the clock, and then when this happens, the next statement is going to be executed. Basically, Q gets the value of D. Now let's just see how we can improve upon this design. Let's just say we want to create a resettable D flip-flop. So if you remember from before, for resettable flip-flops we had two different designs. One was a synchronous resettable flip-flop and the other one was asynchronous resettable D flip-flop. So for the asynchronous resettable flip-flop, anytime that you got the reset signal, you had to reset the flip-flop. But for synchronous resettable flip-flop, you had to still wait for the positive edge of the clock. So for the module that is defined for a synchronous resettable flip-flop, we have for the inputs a clock signal, a reset signal, and then we have the data and Q output. So inside always FF, since this is a synchronous resettable flip-flop, the sensitivity list only contains the positive edge of the clock. So anytime the positive edge of the clock happens, we need to check whether the value for the reset signal is 1 or 0. Because if the value for reset signal is 1, that means that we want to reset the flip-flop, which means the output needs to become 0. On the other hand, if the reset signal is 0, that is when Q gets the value for D. So for doing that, what we do, we actually use if-else statements inside the always FF. So if reset, that means that if reset is true, Q gets 4 bits of 0. So basically it gets a binary value with all the values being 0. Else means that if the reset is not 1, Q gets the value for D. So again, it is very straightforward, similar to the way that we describe the functionality of the flip-flop. We actually use the same description to implement the flip-flop. But now let's say we want to create an asynchronous resettable flip-flop. So one thing that you might guess should be changed is that this sensitivity list now should include the reset signal as well, right? Because for the asynchronous resettable flip-flop, as soon as the reset signal also becomes 1, we want to do the reset. We don't want to wait for the clock. And that's exactly what we need to change. In addition to the positive edge of the clock, now we have to include the positive edge of reset too. So now any of these things happen, the following statement will be executed. So if the positive edge of the clock happens, the following statement checks the value for reset. If we are still in the reset state, basically if the reset signal is 1, we reset the flip-flop or we make the output 0. Otherwise, Q gets the value for D. Similarly, when the reset happens, basically we have the positive edge of the reset, this statement is going to be executed. So if you look closely at the synthesis, these two designs are very similar. So this is the asynchronous resettable flip-flop. This one is the this one is the synchronous resettable flip-flop, and this one is the asynchronous resettable flip-flop. The only difference that you see in the figure is that the reset now appears to be entering the block from the bottom, right? And that is basically to kind of distinguish between the data that is dependent on the clock and the data that is not dependent on the clock. So as you can see here, we have the clock signal, and both the data and reset are dependent on the clock to be reflected at the output for the synchronous resettable flip-flop. But for the asynchronous resettable flip-flop, the data is still dependent on the clock, because unless the rising edge of the clock comes, this data won't be reflected at the output. But the reset is not now dependent on the clock, and that's why it is shown as entering from a different side of the block. And that's how you can distinguish between a synchronous and asynchronous resettable flip-flop. What if we want to even expand this design a bit more? We want to have an enable signal too. So if the reset signal is 0 and the enable is 1, then we want to change the output or store a new value. Otherwise, we don't want to do that. So in this case, we have the clock signal, the reset signal, D and Q, but we have this additional bit, the enable bit 2, that we need to check as well. So this is an asynchronous resettable flip-flop with enable signal. So we have always FF. As for the sensitivity list, we have the positive edge of the clock and the positive edge of reset. So any of these two things happen, we should be executing the following statement. If reset is 1, that's when we want to reset the flip-flop. Else if, basically if reset is 0, we need to check whether the value for enable signal is 0 or 1. So if the value here is 1, that's when Q gets the value for D. But on the other hand, if the value for EN is 0, or the enable signal is 0, basically nothing would happen, and we wait for the next rising edge of the clock or the next rising edge of the reset signal. What about latches, right? Because latches may be useful in some designs as well. So there is a specific keyword for designing latches in System Verilog as well. So here I want to create a D latch. If you remember, latches and flip-flop, they were different in the way that they interacted with the clock signal. So for latches, as long as the clock signal was 1, the output would get the value for the data input. But for flip-flops, only on the rising edge of the clock or on the falling edge of the clock, the output would get the value for the data, and at all other times it preserved its previous value. So for creating a latch, we have only a clock signal, and then we have the data input and Q output. So the keyword that we will be using for creating latches is always latch, and as you can see here, there is no sensitivity list anymore. However, what we have is that any time that clock signal becomes 1, Q gets the value for D. So as you can see, since we are not sensitive to the positive edge of the clock, we don't have to include it as a sensitivity list. But what we can do is that we can just say this process is always looking for the value for the clock. If the value of the clock signal is 1, Q gets the value for D. And at all other times, Q remained at its previous value. So even though it is possible to use latches, right? But generally it is preferred to avoid latches because flip-flops give us more functionality. But sometimes what happens is that because of the way that we code things, we may end up having latches in the final synthesis that we didn't intend for, right? And that has to do with all the additional delays that we may have to include and the glitches that it might happen. So you should always be on the lookout to see if in your final synthesis you end up having some latches that you didn't intend, right? Of course, this is going to be for more advanced users. For us, it is enough to know how we can create latches and flip-flops using System Verilog.